Hello, everyone, to today's online seminar on interval methods in control engineering. And it's my great pleasure to have with us today Christophe Jermann, who is assistant professor at the Université de Nantes in France. And he's assistant professor since 2003. And his research interests are mostly global optimization, numerical constraint satisfaction, and applications in various domains like robotics, CAD, and also computational chemistry. And we're now looking forward to your presentation on the approximation of the inverse of a function near an extremum with bounded approximation errors. Christophe, the floor is yours.
Thank you very much, Andreas. And thank you first and foremost for inviting me to this seminar. I'm very happy to be able to share the research we are conducting in Nantes and share it within this seminar. And so this research was performed with two colleagues, Alexandre Goldstein, Thomas Gouillet, who are also working in the same research team, OGRE, in our lab, LS2N, where we develop essentially global optimization and interval-based solving methods. And so, as you said, my talk will be about approximating the inverse of a function near an extremum, with some bounds, guaranteed bounds on the error of approximation. So the talk will be in 5 parts. First, I will give a brief motivation linked to interval computations, then describe the problem itself, then the method we have used to compute the approximation. And we'll see that we don't need the formal definition of the inverse of a function to compute its approximation. And then show how we can obtain some upper bound on the approximation error, and finally some conclusion and future works. So, as you may know, in interval-based constraint solving, well, at least from the constraint programming community, we use some contractors. And for instance, the HC4 contractor is based on some forward and backward phases, where within the forward phase, a function is evaluated. So, say this graphic. I don't know if you see my mouse moving on the screen.
Yes, we see it.
Okay, so this is a good way to show what I'm talking about. Thanks. So if we first evaluate this function s of x on a given interval, the gray one in x, then we can obtain some interval for the image of s. But then if by means of some other contraction, we have a reduced interval for this image, we can project it back on x and obtain a reduction on x. And this is exactly what is used in this kind of operators to contract the domain of variables. So having reduced domains for functions or for constraints, we obtain reduced domain for variables. So for once, I will start the presentation by some results, which is not quite traditional, but it was our motivation behind this work. So in fact, we are considering some function. I will talk a bit more about it later on, which has this form. So you may recognize the entropy function. And so this is a function which appears very often in some expressions in some domains. And because of that, we were considering the possibility of using a specific operator for this function instead of just its arithmetic expression. So if we use the contracting operation just using the expression itself, then it will involve the reverse operators, which are defined, well defined in the IEEE standards on the expression tree of this function. Whereas if we use a specific operator, then we can use a polynomial approximation of the inverse of this function to perform the projection operation. And I immediately show some interesting results. We have just drawn at random 1 million boxes with every time the same x interval, but an image y which is taken at random within the image of this initial interval. And we just apply the HC4 contractor using A, the standard method, and B, the polynomial approximation at degree 8 derived method. And we can see that not only do we reduce the computation time, not by so much, but we improve a lot the contraction which is obtained. And so this was the initial point for this research. So in the beginning, we were building this approximation more or less by hand or using some tools, and we have ended up with the method I will be presenting now. So what is the problem at hand? So sorry, I have a small window in the middle of my presentation. Okay. So what we consider is that we have a function which has an extrema within the considered domain, and without loss of generality, we'll consider that the minimal value, so first that it is a minimum, second that the minimum value is 0, and it is attained at x equals 0. So the optimal value and optimizer are both 0. So the function could look like that. And we consider it within a given interval. And we have an additional assumption that this is a strict minimum and there are no other stationary points, within the same interval. So we'll try to build an approximation around this point. So what we do first is that we just consider half the domain. We split it at 0, and we'll consider only the inverse on the positive branch. So since it is strictly increasing on this branch, we can compute, well, the inverse first is also strictly increasing, and the maximum is attained at the bound of the interval. And the problem we consider is to find some function g of y, which is supposed to represent the image of f by x, of x by f, sorry, and a corresponding bound delta, so that, as you can see on the graphic, maybe it's more talkative, the function g remains within a delta neighborhood of the inverse of f. Okay, so formally, for all y's within the image domain, the difference between the inverse of the function on y and j of y is less or equal to the delta. So the difficulty in this problem is due to the extremum, because at the extremum, the inverse of the function has an infinite slope. And because of that, the polynomial approximation, for instance, has a very bad conditioning. So for instance, here we consider the approximation of square root of x, which is the inverse of square of x, at 2 different degrees, 15 and 20. And you can see here the distribution of the coefficients. So the AI are the coefficients in the approximation, polynomial approximation, and the difference in order of magnitude between the largest coefficients and smaller coefficients, which indicates that the evaluation will be very sensitive. And second, that the error function, so the difference between the inverse function square of x and the polynomial approximation, is not much improved by going up to 5 more coefficients in the polynomial approximation. So this indicates the sensitivity of the problem due to this extremum. So what we will do is just apply an operation which will make things a bit better. So instead of approximating our function f, what we'll approximate is the capital F function, which is just the square root of f. And using this operation, the behavior around 0 becomes a lot more slow, I would say. The fact that the derivative goes to infinity becomes slower, and we can approximate better closer to zero. But still, we'll see that it remains difficult to attain zero. And so if we do so, and we obtain a polynomial approximation P of the inverse of our capital F function, then it will be an approximation P, which is not exactly polynomial because it will be expressed in the square root of y instead of y. So it is a pseudo-polynomial approximation we'll obtain with some half degrees in it. Every odd degree in the polynomial will have some square roots. So let me go back to this function I talked about in the introduction. So this function is called the Gibbs entropy function. So it is linked to the entropy function by Shannon. And it is used in thermodynamics, for instance, to compute the binary relative energies of components in binary alloys, depending on their concentration, relative concentrations. And so x and 1 minus x in this case represent the relative concentrations, whereas the logarithms and the form of the expression represent the entropy in the system depending on the relative concentration. So this function s of x is evaluated, is considered between 0 and 1 excluded, of course. And it has a minimum at minus log 2, and it is attained at x equals 0.5. So the first thing we'll do, because this function not only has a minimum, and we would like to compute its inverse, and around the minimum it's complex, it's complicated, but also it has an infinite slope in the function itself around 1 and 0. And so because of that, we'll remove a small slice, the portion in red here, around this portion. So we'll try to address the approximation of this function just between 0.05 and 0.95. So we exclude 0 and 1. Second thing is that, as I said in the introduction, we will just center the function and place its minimizer at its minimum at 0. So center the minimizer and the minimum at 0, and send the function f, capital F, that we will try to approximate is the square root of this function s of x plus 0.5 plus the log of 2 in the domain, and we consider only the positive branch, 0.45. And so the graphic is like the one you see on the right-hand side. So our goal is to compute some polynomial approximation of this, of the inverse of this function capital F. And doing so, we hope to obtain a good approximation of the inverse of our function s. And it will be just the application of our polynomial approximation p, but with a slightly different variable, just to put back the minimum at the right place, and with an additional term for the minimizer modification. Okay, I didn't say at the beginning, but if there are questions while I'm on some slides, just feel free to interrupt. Okay, so what's the state of the art with respect to this specific problem? So computing the inverse of a function near an extremum. Well, in fact, we didn't find any specific reference dedicated to this problem. Of course, it can be addressed using straightforward methods to compute the inverse of, for instance, Newton iterations to evaluate the inverse of the function. And we have found within the Mathematica software a function, but it is undocumented, that can perform such computation. But, well, it's not in line with our objectives, because what we want is to be able to compute our own approximation with some flexible requirements. We want to be able to choose the degree, to choose the error, to tune the approximation with respect to the number format that we are considering for evaluation, and projection, etc. And second, we want an automatically verified error bound on the approximation we have obtained. So in fact, there is a software that can perform such things, and it is Solia, which was developed by Chevillard, Joldes, and Lotte in 2010. And it is an environment which is larger than our purpose, because you can derive many, many things, and it is dedicated to the development, basically, of many different numerical codes, and it uses computations with arbitrary precision. So you can obtain a very, very fine, very thin bounds and very good approximation using this software. So I will show a bit later how we used this software in order to obtain our approximation. So how do we compute this approximation? So if we consider the approximation problem itself, then we want to compute this polynomial p, that is to obtain the coefficients a within this expression. So choosing the degree is out of the scope of our research. We consider that we know the degree, and we want to minimize the error, which can be defined as the maximum over the domain for y of the difference between our polynomial evaluated at y and the inverse of the function capital F evaluated at the same value y. So we maximize this error, and we want to minimize over all a's this quantity. So this is a classical minimax formulation for an approximation problem. But in our case, we don't have f minus 1. What we have is s in the case of our application, or the small f. So what we will see is that if we just consider the change of variable where x is just the pre-image of f of y by f, then the minimax formulation in x becomes the following. And in this case, there is no more evaluation of the inverse of capital F in the problem. We just need f and the domain for x, of course. So this gives birth to a linear semi-infinite program, but it is not exactly in the form of function approximation, and then standard function approximation problem methods cannot be directly applied, but instead some standard exchange algorithms may be applied. So if we consider again the problems that we are handling in this case, maybe I come back to this formulation, you see we are somehow approximating x, so identity function with a polynomial, but whose variables are not the y's anymore, they are functions of x. So this is something that is known also in approximation theory, because we can always choose a family of function and perform an approximation with respect to this family of functions. So here we consider the family of function phi of I, which is just the power of our capital F function. And then the polynomial approximation P of f of x is something that has these a coefficients in it and uses this family of function. So this is again a function approximation formulation. And it amounts to approximating, as I said, the identity function x with a specific family of functions. And for this problem to be a valid approximation problem, it has to satisfy some conditions. And so we were able to check that in our case, the conditions are satisfied. So the family of function has to satisfy the hard conditions. And because of the nature of the function near the optimum, this can be shown to be satisfied, which in turns implies that the system of function phi is a Chebyshev system of functions. And this is a result from a famous Müller book. And this means that this problem is a valid approximation problem, meaning that if we obtain an optimal set of coefficients A star for this approximation using the family phi I of functions, then it will be also optimal for our initial problem. The same coefficients can be used for the polynomial approximation of the inverse. Okay, so how could we achieve that? Well, fortunately, we didn't have to program all that. It was already embedded in Solia. And we just have to input a small program, as you can see here. We define our function. We define the function S in our case for the application. We define its adaptation, as I introduced in the beginning, so the square root of f of s of x plus 0.5 plus the log 2. So we shift the value and apply a square root on it. Then we build this family of function phi, which are just the powers from 0 to 8 of the function f. And we apply Remez exchange algorithm to compute the approximation of x using the family phi on a given domain dx. But here you can see there is a small detail that we could not enter the domain we wanted. We could not put 0 there because in this case, internally Solia has some checking about the hard condition. And because of the singularity of the derivatives, it is not able to prove numerically the hard conditions if 0 is included. But because this software uses arbitrary precision, we could enter a very small number and still obtain an approximation. So what we obtain is an approximation J formulated as follows, and we have our coefficients, so we could put them back into our polynomial P, which is an approximate inverse of the entropy Gibbs entropy function applied at these shifted points. Well, this detail is not completely satisfying because we obtain an error. You can see it here. I will just talk about it in the next slides. But it is not proved because the 0 could not be included. So it is not a rigorous upper bound on the error for the approximation on the whole domain 0 to 0.45. So how do we bound, now that we have an approximation, we obtain an approximation, how can we bound the error on this approximation? So if we consider the, if we consider the error function, it is formulated as follows. We have our function which amounts to x, and we subtract p evaluated of the square root of f of x. But if you just derive, this function, you obtain the following generic formula. So in the generic cases, this derivative is indeterminate at 0 because of our extremum. So f of 0 is equal to 0, and also the derivative is equal to 0. So the numerical evaluation on an interval that contains this extremum will not be possible or will not bring any useful outcome. And any algorithm, by this way, any algorithm based on a numerical enclosure of the zeros of the derivative will fail. And this is indeed what happened within Solia. So if we use some functions which are already implemented in Solia and able to compute the norm of an error between an approximation and a function on a domain, and we try to apply it to the domain 0.5 to 0.95, it just fails. If we use it with a small epsilon, and we have seen that we can use as small as we want an epsilon, then it works. And with some given epsilon, we were able to achieve this kind of bound. But it's still not fully proved to be rigorous on the whole domain. So what we thought we could do is just choose an optimization model to solve this problem. So for this purpose, we used IBEX-opt, which is an optimizer, global optimization algorithm built upon the IBEX library, which was developed in Nantes, and a lot of other groups in France. And it implements an interval branch and bound, uses constraint propagation without derivatives. Well, at least it can. It can also use Newton methods, but it can use constraint propagation without derivatives. And it uses rigorous linearizations. And the problem we input to this solver is to find the maximum of the error subject to the fact that the derivative goes to zero. So of course, as I said before, any method that tries to do so because of the indeterminateness of the derivative around zero will fail. But still, because of the splitting method, the bisection method within the solver, there will be just unresolved boxes which will be accumulating around zero. And because the widths of these boxes on X will converge to zero, the evaluation pessimism on the boxes will also converge to zero. And this way, we can obtain an upper bound, which is this time guaranteed because no box is above, and which has almost the same value. You can see just, well, 0.1, well, 0. Well, 10 to the power minus 8, sorry, approximation. And so in the end, what we obtained, sorry, I have not concluded. Well, I could conclude there. We have obtained an approximation of our function, of the inverse of our function S, with a good polynomial at degree 8, which is not proved to be the optimal one because it could not be proved on the whole domain. But still, we could obtain a guaranteed upper bound on this approximation. And this is sufficient for our application. Now we can use this polynomial within our contractors to build a reverse operator for the entropy, Gibbs entropy function within IBEX. So what we have done here is to propose a general procedure to achieve this computation, obtaining the inverse of a function in Extremum. And in the future, what we'll try to do is to refine this work by considering not only the approximation error, but also the evaluation error, which was something that was already done in 2019 by Arzelier, Bréard, and Joldez. And also use other families of functions because we have realized since then that applying well, somehow brutal application of a square root over the function itself is not quite standard in approximation theory. Instead, what they use is powers of the function multiplied by just the square root of the function and not immediately square root of the function elevated at some powers. Well, it's almost the same, but not completely exactly. And also to test our approximation and validate it in the context of our solver for the computation of phase diagrams. So this we have already started to do, and unfortunately it's not so interesting at the moment because this is just a single operator within a much more complex problem, and the gains, unfortunately, on the evaluation or on the projection of this function are very interesting, but it's not sufficient to outperform previous results. Okay, thank you very much. And if you have questions, I will be happy to try to answer.
Okay, then many thanks, Christophe, for a very interesting presentation. And yeah, this is also exactly the question that I would like to ask. Is there anyone who wants to ask something? Okay, I do not see any raised hand. If there is a question, please unmute yourself and just go ahead. Yeah, in the meantime, maybe let me start with one or two questions. The first question that I have is, do you have, let's say, some kind of generalization also to multivariate functions?
Well, in fact, the work I just presented was already done something like almost 2 years ago. And since then, we have not pursued so much the future works that we were describing there, but instead considering multivariate functions because of our application, because the optimizing the projection of the entropy function within our problems was something we expected to be useful, but it was not so much. Whereas there are other functions, but unfortunately, they are multivariate, and for these ones, it could bring a lot of things. So we have just built some approximations by hand, more or less, not fully guaranteed at the moment, and it seems to be promising. So because of that, we have concentrated our efforts over this direction. So you have some no's, as we say in French,
Yeah.
and this is something we are currently working on.
Yeah. Okay, great. The other question that I have, the expression that you had for the approximation, I think it was on your slide 12, reminded me of something else. Yeah, exactly the formula number 3. Uh,
Mhm.
what it reminds me of is that, for example, if you want to determine the exponential of a matrix, you could easily write this with the help of the theorem of Cayley-Hamilton in the form of a polynomial.
Okay.
Yeah, the more or less the basic theory behind this is that practically every square matrix satisfies its own characteristic polynomial.
Mhm.
Yeah, and what I'm wondering here is this something that you could also make use of, for example, for some special kinds of approximations? Because, for example, the theory of theorem of Cayley-Hamilton could be applied for computing determinants. It could be applied also for determining matrix exponentials, as I just mentioned. Yeah, and some other, let's say, expressions that could all be referred back to the evaluation of a polynomial function, in fact.
Mhm. Okay, so this is an interesting track, but unfortunately, I don't know much about matrix exponentiation, so I cannot imagine at the moment the possible connections between these two problems. But this would be something interesting to have a look at and see um, if the proximity that you see within the equation can go further than just a syntactic
Yeah,
proximity.
because the thing that you would have there is those phi's that you have in the equations are
Mhm.
then just the powers of the matrix for which you want to compute the exponential.
Yes.
And this is practically what you have written up there. You have this phi I, which corresponds to some power of f.
Mhm.
Yeah, and yeah, I can provide you with a reference.
Okay, I will have a look, definitely. Well, the thing
Yeah.
in our context is that we are not so much interested in computing the phi at some points, but instead of computing the a's. But probably you need the same thing to obtain the exponential, isn't it?
Yeah, and for that you would need to evaluate the characteristic polynomial of a
Mhm.
matrix. And this could also become quite complicated if you have, for example, high-dimensional system models.
Mhm.
You need to determine determinants of very large matrices of large dimension, and this could also easily become, yeah, computationally complicated, especially with respect to round-off errors. That could definitely complicate the things.
Okay. Okay. Um, so if you can send me a reference, then I'll
Yeah.
definitely have a look and try to induce some connection.
Okay, sure. Then let's have a look at again at the list of participants. Is there anyone who has any further question? Yeah. The only statement that I've seen in the chat is that Luke is thanking you for the interesting presentation.
Okay, thank you, Luc. Merci, Luc.
Okay, if there's no further question, then thank you again for your inspiring presentation.
Thank you.
And yeah, We're looking forward to the next online seminar. It is still not clear whether we'll have a presentation Friday next week. If not, if we do not meet Friday next week, then we'll meet again in January. And in this case, I wish all of you a happy and nice Christmas holidays, and also happy New Year. And see you, all of you, soon in one of the upcoming seminars.